So this is the summary for analytic solution method of first order differential equation that we've learned so far. So for a given ODE that we want to solve, and at the end we want to have solution of the differential equation. As we noticed at the end, everything was separating variables, separation of variables. So you want to make, no matter what type of differential equations, all you want to do is utilize every method to end up with separation of variable, and then you get solution by the integration, right? So if you have an ODE you need to solve, the first thing you need to think about it is if it's separable right away or not. Okay, so if it's separable, then you just do the separation of variable. If it's not separable right away, then the next thing you could check is if it's reducible to separable form, like to here. If you can apply the reduction to separable, let's see if it's reduction to separable, and that kind of formula is this: some functions, some differential equations have in this form can be reduced to separable. So you could check if it looks something like that. Once it's a reduction to separable, then you go to separation of variable again, and then you get the solution. Okay, here you have the changes of variables y over x to u, and then you apply that. And the next type is exact form. So if the equation is given something like this, and y is 0, it's given like that, then you would need to check the exactness of the equation. So if it's exact, with the dm over dy is dn over dx. This is the exactness condition to check it, and if it's yes, then you could solve in using the method of exact ODE method. Okay, and at the end, this one is also separating the variables to get the solution. So in the method of exact ODE, you use this relationship, dy is n, okay, to get u by integrating this and using the other relationship. On this exactness condition check, if the answer is no, then you can try to find the integrating factor f to see if the multiplication of that integrating factor with the differential equation make the equation exact. Okay, so finding the integration factor is having this relationship fp over dy dfq over dx, and then if you find the f from this, you multiply this f into the equation, and then the equation becomes exact, and then you could apply the exact method. The last differential equation type is the linear equation. Okay, y prime plus p of x y is r of x. This kind of form of equation you're dealing with, you first check if it's linear, And if it's yes, you could check homogeneous by knowing the input. If it's yes, then you have method for homogeneous linear equation method, and that eventually goes to separation of variable 2. And if it's not homogeneous, no, then it's non-homogeneous linear method. That goes to that. If the answer for the linear is no, then it will be nonlinear case. And there's not much, type that we can solve for the nonlinear case, but in a certain case, like for some case like Bernoulli equation, looks like y prime plus p of x, y is g of x times y to the a. Particularly in this type, then we can reduce it to linear system, reduction to linear. Okay, and that can be solved like this. So actually this type of equation is Bernoulli equation. Then we substitute u y to the 1 minus a, and then we plug it in, and then we calculate the formula, and then we get the separated variable, and then we can get the solution. So this is the whole overview or big picture of analytic solution method for FODE. This is quite complicated, so if you try to memorize them, I think you simply cannot. And if you want to memorize the formula, you'll forget it easily. So trying to understand the basic concept of the methods and follow the logic of the development, then it won't be that hard to really follow the method according to the given differential equations.